All right, well, this is still Tuesday, June 29th, 2021, Math 3 spring term after the halfway point of the period. And what I'm going to try to do is get you even better on dealing with exponential functions. And we're trying to move towards an understanding of uh, logarithms, inverse functions, exponential growth, decay, all that good stuff. That's what I have to say. So let's consider a function like y. Why do I have that color? Because I didn't change it from last time. Ooh. Okay. Suppose I have a function like y equals, something, well, the 1/2 that we just did. 1/2 raised to the x power, where if this is a half-life problem, then x is the number of half-lives. And as I showed you before we did this money problem, a half-life could be a real number. It doesn't have to be an integer number. It doesn't have to be a whole number. What if I were to try to make a graph of this, a sketch? Well, what you should do in a situation like that is maybe set up a table of values. And on your table of values, put in a few points so that you have a feel for what the curve is doing. So almost as, the default values. How about we do -3, -2, -1, 0, 1, 2, 3. And for each one of these values of x, we calculate the value of y. All right, well, for the first one, 1/2 raised to the -3rd power. A property of exponents is that a negative exponent is 1 over the number to the positive exponent. I didn't quite say that correctly. A number raised to a negative exponent is equal to 1 divided by that number raised to the positive of that exponent. So 1/2 to the -3rd power can be thought of as being 1 divided by 1/2 to the positive 3rd power. And so now you have to ask yourself, what is 1/2 times 1/2 times 1/2? Because that's what 1/2 to the 3rd power means. Well, 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. So 1/2 times 1/2 times 1/2 is 1/8. Now you love fractions. I know you love fractions. What is 1 divided by 1/8? Okay, so now we're going to use the property that 1 divided by 1 divided by some number a is equal to that number a. Okay, so 1 over 1/8 is equal to 8. Ta-da! And I have a dot to plot. When x is equal to -2, it's going to be 1 over 1/4, which is 4. When x is equal to -1, it's going to be 1 over 1/2. 1 divided by 1/2 is 2. I thought I would make that a warm-up question today for you. All right, next one. 1/2 to the 0 power. 1/2 to the 0 power is 1. Any number other than 0 to the 0 power is 1. So this is 1. And now we deal with positive exponents. 1/2 to the 1st power is 1/2. When x equals 2, it becomes 1/2 times 1/2 is 1/4. When x equals 3, it becomes 1/4 times 1/2, which is 1/8. All right, we have enough dots to plots. Let's set up some graph paper. let's say this is the positive x-axis. Let's say that here's the positive y-axis. I'm missing the grid mark a little bit, but there's the origin. At -3, I'm using a scale of 1 per square. So here's -1, -2, -3. I go up, and I'm using the scale of 1 on the y-axis as well. So I go up 8 units from the x-axis. 1, 2, 3, 4, 5, 6, 7, 8. Whoop, maybe I should change colors, huh? Whoop, there. At x equals -2, I go up 4 units. 1, 2, 3, 4. At x equals -1, I go up 2 units. At x equals 0, I go up 1 unit. At x equals 1, I go up half a unit. 2, a quarter of a unit. 3, an eighth of a unit. Okay, I've plotted plenty of dots that you should be able to see how this behaves. It comes from positive infinity. And as I move to greater and greater values of x, it becomes 1 divided by an ever bigger number. Well, 1 divided by an ever bigger number is an ever smaller number. So this thing approaches 0. Okay, it approaches 0 as it goes to negative infinity. Positive infinity. So it's going to, x goes to positive infinity. Now, y is going to approach the line y equals 0. So y equals 0 is an asymptote in this situation. An asymptote is that straight line that the curve is approaching but never touches. Well, 1/8, 1/10, 1/16, 1/10,000, 1/20 millionth, that is ever and ever, ever closer to 0. It becomes 0.01, 0.0001, 0.000001, but not 0. So y equals 0 is the asymptotic line that it approaches as x goes to positive infinity. Now, where did this thing come from? Well, it came from positive infinity for ever more negative values of x, because we are dividing by an ever smaller number as x goes from -1 to -2 to -3 and so forth. So this thing, if I ask you what is the domain and the range for this function, well, okay, so the domain is from positive infinity. I'm sorry, I'm talking about the range here, aren't I? The domain is how far does it go along the x-axis in a negative direction? And the answer is, okay, it can go to negative infinity. No worries. How far does it go in the positive direction? And the answer is, it can go to positive infinity. So the domain is negative infinity to positive infinity. For the range, okay, this thing has a flat floor at y equals 0. It never touches y equals 0. It just gets closer and closer and closer to it. And where did it come from? Well, it came from positive infinity. So the range in this situation is, I don't even think it's a hard value there. I think it should be open parentheses, 0, comma, positive infinity. There's the range in this example of half-lives. The asymptote is y equals 0. The domain, set of all real numbers. Great. Now, what if I used something other than, and by the way, we would classify this as decay. exponential decay, because the greater the value of x, the smaller the value of y. It decays towards 0 as you go left to right. Let's do another example. Y equals, well, okay, the traditional ones are things like 2 to the x power. What would that look like? It'd be great if you could visualize the answer in your head already. But as always, build a table first and plug in some numbers. How about we do the same set of numbers, right? It's ever so useful to have plotted those dots. So -3, -2, -1, 0, 1, 2, 3. And now for each value of x, evaluate the value of y. Well, 2 to the -3rd power is the same thing as 1 divided by 2 to the 3rd power. I'm using that property of exponents. So 2 to the 3rd power is 8. So this is 1/8. When x is equal to -2, this is 1/4. When x is equal to -1, this is 1/2. When x is equal to 0, 2 to the 0 power is 1. When x is equal to 1, 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. And I'm trusting you have enough understanding to sketch what this thing looks like. So we set up our graph paper once again. I will shift it ever so slightly to the right, I guess. And stick it around here, I guess. Same scale, 1 unit on each axis. And at -3, I'm at 1/8. So -1, 2, 3 is here, 1/8 is there, and it's a positive number. Oh, let me change the colors of my dots. Oh, we'll make it this color. Okay, -3 is 1/8. -2 is 1/4. -1 is 1/2. 0 is 1. 1 is 2. 2 is 4. 3 is 8. 1, 2, 3, 4, up from there. Okay, I've sketched enough dots that you should be able to put it all together. In this situation, this would be called exponential growth because it's becoming larger and larger and larger as x becomes more and more positive. It approaches 0 from the left, but again, it never touches 0. 1 over a big number is a tiny number, 0.000000001. Ah, that's not 0. Pretty close, but no. So this thing, if I were to classify it, and this is what you should be able to do, you should say it approaches the asymptote y equals 0. Actually, as x goes to -infinity. What are the allowed values of x? Well, it can go all the way from -infinity to positive infinity. So that's the domain. For the y values, it never goes, it doesn't even touch 0, and it goes up from there. It goes to positive infinity. So the range in this case would be 0 to positive infinity. These are two examples of exponential functions. There's exponential decay, and basically any number less than 1 raised to the x power is going to be an example of exponential decay. Why? Because you're multiplying a small number by a small number to create a smaller number, which you then multiply by a smaller number to make a smaller number. Exponential growth will be for any situation where the number being raised to some exponent is greater than 1. 2, for example. Well, you double it, and then you double it again, and then you double it again. Well, so it's going to get bigger and bigger and bigger. All right. Now, in your homework, they're going to deal with having you derive the natural number e. Oh boy. For starters, you've encountered the irrational number pi. The Greeks were fascinated by this. They wanted to know what is the ratio of the circumference of a circle divided by its diameter. And they realized that they couldn't precisely measure it. They used physical materials at hand to try to measure it. And they said, well, okay, we're going to approximate it. It's around 22 sevenths. Because they like expressing things as fractions. And so they said, it's roughly like that. But today in modern times, we know, oh no, this isn't 22 sevenths, which I'm curious, what's that on your calculator? 22 divided by 7 is 3.142857143. Oh man, pretty good Greeks. Okay, but today we know it's not exactly that value. Your calculator memory will have it to 10 sig figs, and your calculator says 3.14159.265, and I'm just going to put ... because maybe that 4 is rounded off already. So it's an irrational number. It has no ending, but it's incredibly useful as a number. You give me a diameter circle, I can give you its circumference. I can give you its area. I can give you all this stuff which is useful. Engineers use pi to design the audio system that we're using to communicate with each other right now, when it works. E is also an irrational number. And in your homework tonight, they're going to try to have you approach the value of E by doing a series of calculations. The calculations are similar to the compound interest situation for the bank. Okay, I have so much money, here's the interest rate, it's going to be compounded at this rate. How much money will I end up with? So they're going to use, to derive it, they're going to use an interest rate of 100%. And they're going to start with the number 1. Okay, so the principal value is going to be 1, and the interest rate is 100%. And the first time you do the calculation, they're going to say, okay, suppose it is being compounded annually. Annually means once per year. Okay, once per year. So the formula said the amount that you end up with is equal to the principal that you start with times 1 plus the interest rate divided by the period of time it takes to compound it, close parentheses, raised to the product of the compounding time times the amount of time that goes by. Okay, so what we're going to do is for annually, the time will be equal to 1 year. The compounding rate, when it's annually, that's what annually means. It means you're only going to compound it once per year. Okay, so K is equal to 1. The interest rate, if it's 100%, and that's, I'm sorry, I wrote it as an I. In your homework, they use the letter R to represent it. And of course, that's the same thing, right? So lowercase r, the rate is equal to I, the interest rate is 100%. Well, 100% is 1. And if we start off with a value of 1, then the first time you do this, it's going to be 1 times 1 plus 1 divided by 1, close parentheses, raised to the first power. And this is an equal sign. Okay. You can do this one in your head. You don't need no stinking calculator. What is 1 divided by 1? Oh, that's 1. What is 1 plus 1? Ah, that's 2. What is 2 to the first power? That's 2. And what is 1 times 2? Ta-da! You can check it with a calculator if you have any doubts about my math skills. All right, so there you go. If you have 100% interest rate and you start with a value of 1 unit, after 1 year of being compounded annually, you'll have doubled your money. And that would be great if you could do it in real life, assuming that money is that valuable to it. Now, what if we switch this down and we say, oh, no, we're going to compound it every 6 months? On your homework, some of you mistakenly talked about how many ounces of caffeine you have. The person drank a 12-ounce cup of coffee, but he started with 80 milligrams of caffeine. Don't mix up milligrams of caffeine with ounces of coffee. Oh. So the units matter to me. I will fail you if you don't have the correct units. This unit of 6 months, let's draw this. 6 months is different from this time period of 1 year. You have to put them into the same units. So either turn 6 months into years or turn the years into months. Okay? One way or the other. You got to do it correctly. So in this new situation, this is a new calculation. Let's see. Do I have my pen working? This is a new calculation. It's going to be, the amount that we end up with is equal to 1. So we're starting off with 1. We're doing a new calculation. Times 1 plus. Now, if the interest rate is 100% per year, then in half of a year, the interest rate is only going to be 50%. So this is really going to be 0.5 now. But the period of time over which it becomes compounded is also now half a year. Now, what do we have going on as the exponent? It's the product of the amount of time actually, I think I should express it by saying it is the amount of time it takes to compound things times the total amount of time. The point I'm trying to make is that this becomes squared. Can I persuade you that that is the number of times that it is compounded in 1 year? Think of it that way. The number of times that it is compounded in that 1 year. Well, 0.50 divided by 0.50 is 1. So now, I think I have a wrong answer. right? Because this is going to be a value of 4, and that's definitely wrong. So let's make the claim that that number is wrong. K times T. K is the amount of time it takes to compound. T is the amount of time that goes by. Oh, the 2 might be correct. This might be wrong. I should pause the recording when I make terrible mistakes like this, right? So that none of you ever have any proof of it. 1 over, this is supposed to work out to be 1 over 2. I'll tell you how it's supposed to work out. Let's see if you can correct my mistakes. This should work out to be 1 plus 1 over 2, close parentheses, quantity squared. Okay, now I'm really curious. What do I get in my calculator when I go, what is 1.5 squared? Oh, yeah. It says 2.25. And that is the correct answer when the compounding time is 6 months on an interest rate of 100%. Do I know why it is that value? And I think the answer is no. But I can tell you that that is the right value. I can tell you what the next one should be like. For the next one, suppose you compound it every 3 months. Then this thing becomes A is equal to 1, open parentheses, 1 plus 1 divided by 4, because there are 4 times you're going to compound it in 1 year, or the interest rate is 1/4 of a year. That's the way to put it. Okay. So this is the interest rate. It's 50% expressed as a decimal. If you compound it 4 times in a year, then the interest rate is 1/4 of 100%. And you're going to compound it 4 times. Great. And you put into your calculator, what is 1.25 raised to the 4th power? I wrote n. I should replace this n with the number 4. And I get 2.441. Another correct number. Woo! I'm getting right answers. I'm just not explaining correctly how I get those right answers. I guess I don't like this formula. This r divided by k, I'm really using r, the interest rate, as a decimal value as I do this. What I can tell you is this is the pattern for you to follow. And there's a progression here. So let's look at these numbers for a moment, maybe with some other pretty color. Ooh, pretty. So the first time around, it was 2.00. The next time, 2.25. The next time, 2.441. And where we are going with this is a geometrical progression. Now, I'm not sure how much, if at all, you students studied series and sequences. I have 8 minutes, and I feel like I should try to teach this to you. Maybe I can. And maybe I cannot. I'm pulling out an old Algebra 2 book. Meanwhile, I see Nicholas, your camera's off now. Oh my goodness. Throwing points away just like that. So from this old Algebra 2 book, I'm referring to material that is from chapter 11. Oh, the Fibonacci sequence. Nice. Recursive formulas. Geometry and infinite series. Convergence and divergence. You know, I don't think I can. Woo! Mathematical induction, area under curve. We don't want those things, and that's the end of the chapter. Okay. How to do this to you. Divergence is when the numbers become I don't think I can define divergence. I can define convergence. Convergence is when values approach a single number. This is going to be a situation where that happens. So it's converging. This pattern, if you keep doing it for annual, then 6 months, then 3 months, do it daily, 365, do it monthly, 12 months in a year. Do it daily, 365 days in a year. Don't bother with the leap year stuff. Then do it for the number of hours. Do it for the number of minutes. Do it for the number of seconds. Every time you do that, the number will change by a smaller and smaller amount. It's converging to a particular value. And the educational punchline is it's converging to the irrational number E. So all of this is just an interesting way of introducing you to this irrational number E. When you finally get there, they have an equation that you can use. They call it PERT, right? PERT. I miswrote it, didn't I? You didn't see that. No, you didn't see that. The amount of money that you end up with is equal to the principal that you start off with times E raised to the interest rate times time. This is exponential growth. So that means if I do a sketch, if p is equal to 1, e to the 0 power is 1. So it's going to go through the point 0, comma 1. Let me make this just slightly less sloppy. Let's say that right there's the origin. This function will go through 0, comma 1 if p is equal to 1. And being exponential growth, it will come screaming up from y equals 0, go through that magic point that exponential functions go through, and then increase exponentially without end. So it's coming from negative infinity going off to positive infinity for the domain. For the range, y equals 0 to y equals positive infinity. It starts off hugging the line y equals 0 as an asymptote. And mathematically, this is a situation where you would say it's continuously compounding. So not even once per second, but once per, as small of a division as you want to make for time. It's continuously compounding, growing. And this describes stuff like, COVID growth rate when it first arrived, and other forms of exponential growth, sometimes with life forms, how long it takes bacteria to multiply at a certain rate. Okay, so it's useful. This allows you to calculate how much money you'd have in the bank. Again, if you want to do that as an example, let's say we close by saying I still have my $2,730, and the interest rate is 8%. After 1 year, how much money will I end up with, right? So that's going to be 2,730 times e to the 0.08 power times time of 1 year. Let's see if that works. So 2,730 times, on your calculator, if it's a TI model, it's second natural log, e to the 0.08 power, enter, and it says in 1 year you would have $2,957.37. So keep that in your memory for a moment and look back when we used a different number. I used $3,720. Here I use $2,730. So you can't compare them. I will make the claim, though, that in this situation, the interest rate would be even a little bit better than it was when it was compounded monthly. All right, the period is ended. We have support today from 1 to 1:30. You have an assessment on Friday. You have homework due today. All those horrible things. Some of you never turn your cameras on, which is sad because that means you're choosing to just throw away those points.